today I am talking about conservation of energy. If we want to state the first law of thermodynamics for a system in words, it is time rate of increase of the total stored energy of the system equal to net time rate of energy addition both by heat transfer and work transfer into the system. And this is how we describe it in the variable forms. And this little e here is the specific energy of the system, and which is equal to the internal energy per unit mass, and this is the kinetic energy per unit mass, and this is the potential energy per unit mass. Now, by applying the Reynolds transfer theorem with considering the B of system E and the B little is as E also, it's like when we wanted to drive the conservation of mass, we use B system as mass, and then this time we want to drive the energy equation, so we use B system as E. So if we apply this theorem, and this is the formula that we get, which is let me just elaborate all the things. This one that we know that this is the time rate of increase. So let me say that the time rate of increase of the total stored energy of the system. And this term right here is time rate of increase of the total stored energy of the context of the control volume, right? It's the integral over the control volume. And this term right here is the net rate of flow of the total stored energy out of the control volume through the control surface. Through the control surface. So this is how we define the energy equation till now. And then if I call this equation right here as equation number 1, and this definition of E as equation number 2, and then substitute 2 in 1, we get this formula here. Substitute 2 in 1, right? And in this equation right here, we have heat transfer and work transfer here, right? So the heat transfer and the work transfer are considered positive if they are going into the system and negative if they are coming out of the system. So positive going to the system. I should write it down here. Just give me a second. Yeah, let's write it down here. Positive going to the system and negative coming out of the system, right? And also we can show it through the figures as we can see the Q1 is going to the system, so it's positive. Q2 going to the system, it's positive. Q3 is coming out of the system. It has a negative sign, as well as the Q4, right? So, and then this W dot here is the net rate of work transfer into the control volume, right? We also call it as power. So we call it as power because the work is dot product of force and the related displacement, right? It's just force times the distance. So let me just write it down so we know that work. Let me change the color. So we know that work is force times the distance. And now the power, we say that W dot is the net rate of work to the work control volume, right? So the net rate is kind of mean that over time, right? So if we divided S, which is the distance, by time, it's going to give us velocity, right? Then W dot is force times velocity, which is the definition of the power. So this is power, this is work. So let's go to the next part, which we now try to elaborate what is the heat transfer to our system and what also our work transfer represent. So the heat transfer represents all of the ways in which energy is exchanged between the control volume contents and the surroundings because of the temperature differences. So which includes all of our type of the heat transfer, which radiation, condition, and convection. And if we consider our system, which is adiabatic, so it means that the heat transfer rate is going to be 0, which happens in lots of an engineering application. And then the work contributions include the shaft work, which is the shaft work is the for example, we have a rotating shaft in which the power transfer, which is W dot of the shaft, is related to the shaft torque that causes the rotation um, mm, T shaft, and then the angular velocity of the shaft omega, right? So it means that we have a shaft fork because of the shaft torque that we have that causes the rotation. Also, we have a work that is due to the exerting normal stresses over its distance, and this type of work is transfer across the control, uh, which I'm going to explain more just here. So let me just go to the other work that we're gonna have. The other work that we have is due to a fluid exerting tangential stress tau along a surface. So now let's get back to our normal stress forces that we have. So I just said that it's due to the fluid pressure at the control surface. And if we have this pipe here, and we have opening here and here, right? And the flow is coming in and going out, and this is our control volume. Try that. Let's just make it better. So let's say this is our control volume, right? Then it means that at these two openings, we have sigma, right? And the sigma is minus P. So let me just write it down here that it's just happening only at openings. We talk about it. Talk about this forces at the linear momentum as well. Because here, right, the velocity is not zero if we look at this equation also right here. So this is why we have the normal stresses at the opening So let's go to the next definition, which is the tangential shear stress. So tangential shear stress is happening due to the viscosity of the fluid at the control surface, right? So if I have, just let's say I have a pipe like this, and then this is my control volume. So if you remember, we have shear stress all near the surfaces, right? And then if I have a control volume, For the control volume, the fluid particle velocity is zero everywhere on the surface of the pipe. So then there is, because the velocity is here, because of that no slip boundary conditions is zero, right? So the velocity is zero uh, on the surfaces, right? And so tau dot v is going to be zero because we don't have any velocity, right? And then it means that we don't have mm, any velocity due to of the shear stress, right? And also, if we select the control surface so that it is perpendicular to the flow particle velocity, then the tangential stress force is also perpendicular to the velocity, right? So therefore, the tangential stress for transfer is going to be zero also on that part of the control surface. So still, if we say that 2 is perpendicular to the V, then also tau that V is going to be 0, then it means that the work due to the tangential shear stress is going to be 0. Then now let's see how we can get this equation here. So let me just name some of the equation that we have. So let's call this one equation number 3. So this one right here is number 3. And then this one right here is number 4. And by the way, so this is the whole work transfer that we have. So we have the work due to the shaft, which is kind of in rotary devices such as turbines, fans, and then we have and this one we just see that it's going to be 0 in all of the control volumes. And then this one is also this one right here is also happening only at the openings. So now let's see how can we get this equation here. If now I substitute equation number 4 into 3, we get this equation here. And then let me see. Okay, and now if we substitute E, that we have it right here, which is number 2, we're gonna get our energy equation. Right, this is E. And now one of the important things we need to remember here is that the velocity here is not a vector anymore. This is magnitude. Magnitude, right? So this is the magnitude of velocity because that is what matters for kinetic energy, right? So we are cared about how much kinetic energy crosses the boundaries of our flow. So it's just the magnitude of the velocity at that point. So let me just write it down better. So this is E and this is, oh, not this, I mean this velocity right here is the magnitude. And then if we go a little bit further right here and talking about the application of the energy, so we know that this term here, it depends on time. So if we have a steady state flow, it's going to be 0. And this flow right here can be non-zero only where fluid crosses the control surface, right? And this is the integral over the control surfaces. And then also this equation here that we have, if we consider the uniform velocity, we know that we can just take it out of the integrate, so we can have this formula, and then if we only have one stream in turning and leaving, like this shape here, there is like a small stream tube, and then the mass flow rate going in from here, and then from this section the mass flow rate coming out, right? So if we have only one stream, so this sigma here, right, there is no sigma anymore, so this is for flow out, there's just one, and then this is for flow in. And then let's go to the number 5. So this enthalpy is just a definition, and which is H equal to U plus P over rho, right? And then this is what with this, and this is associated with the energy as fluid crosses a control surface. And now if we use the enthalpy to kind of show our energy equation, so this is right here, which we just substituted with U plus P over rho. We have this formula that is commonly used for compressible flow. And then number 6 is when we have, we call it the energy equation for a steady in the mean flow. So there are some assumptions that we made to get this formula. The first one is the steady in the mean flow. And then what it means is that when the flow is steady in the mean cyclical, so for example, the velocity and pressure at fixed location near the rotating blades of a fan are unsteady, right? But the but it's going to be steady at the upstream and downstream of the machine. So this is what we call it, steady in the mean flow. And then we consider this by one-dimensional, or a definition of it, just let's say uniform at control surface, right? And then another assumption is constant properties, and then there is only one inlet and one outlet, so meaning that m dot in is equal to m dot out is equal to m dot, right? And this is for both incompressible and compressible flow. Incompressible, oops, compressible and compressible. So we can use it for both of these flows. And then next is even more simplified equation than this one, and this is when the shaft power is zero, and if we say that the flow is steady throughout the control volume, then the shaft power is zero. I mean, in other words, the fluid machines mm, involve locally unsteady, but then when we say that it's steady, then it means that we don't have any work. So these are, I mean, I know there are lots of formula right here, but we are just wanted to make sure that you understand all of the terms. So this is why we just slowly getting to this formula right here, and even we are going to simplify it more. But just remember that whenever we simplify equation, it means that mm, it's just for a specific problems, not for all of the problems in fluid mechanics. So let's go to the next topic, which now we want to compare the energy equation with the Bernoulli equation. Now let's divide this equation right here by mass flow rate. So if we divided this equation right here by mass flow rate and rearranging the terms a little bit, this is what we get. And then, oh, I'm sorry, not this by that. I mean this equation, if we divide it by mass flow rate, this is the exact one right here. And then if we divided it by mass flow rate, this is the equation that we get. And then this last term right here, this last term right here, we call it loss. And note that this Q right here is the heat transfer per mass flow rate, which I just defined it here. And then let me see what other terms we have. And also, and this equation involve energy per unit mass and is applicable to one-dimensional flow. I just don't want to you guys forget this assumption that we get. This is why I repeat it again. So this is for a one-dimensional flow of a single stream of fluid between two sections, or the flow along a streamline between two sections. So now if we just if we compare it to the Bernoulli equation, we can just see that the differences is this loss, these terms that we call it loss here. So this is our Bernoulli equation, right? So then it means that if we have if we just consider the negligible viscous effects, means frictionless flow, then this equation become to be Bernoulli's equation. And then it means that we can use Bernoulli's equation to describe what happens between two sections in the flow as we did before, right? So let's talk about these terms a little bit. So we just call it its loss, right? So these terms here, right, are Ideally, we can consider this is zero, but it's not zero. It's for a steady incompressible flow with fraction, this is more than zero, right? So this is, and we always try to minimize this loss. Um, Actually, this is kind of the goal of the fluid mechanics design, right? Um, and then if we go a little bit further and talk about the mechanical energy equation. So just one more thing before I go to the mechanical engineering. So right here we call this one loss, right? So then it means that this term here is considered to be the useful energy, right? So this is the useful energy, and this is loss. So now let's go to the next topic, which is the mechanical engineering equation that we can just write this one in terms of energy per unit mass. So this is now what we have here. This is the equation that we have, and this is one of the important equation in this topic. And then this is why I just want to say that why we simplified this. I mean, the important group of the fluid mechanics problems involve one-dimensional, incompressible, steady in the mean flow with the fraction and shaft work. So I mean, I know these are the assumptions that we made, but it just like these assumptions we can, I mean, it's not we idealize our situation and our problems, but it can simplify how we can solve the problems. So, for example, we can use these things when, uh, for example, the density flows through the pumps, through the turbines, through the fans, and then for this kind of flow, we can use this equation, right? So this is kind of a form of the energy equation for a study in the mean flow that is often used for incompressible flow problems, right? So it is sometimes also called the extended Bernoulli's equation because of these two extra term right here. So now if we multiply this equation by rho, this is how, and this is another form of it. I mean, it's not different. You can use, I mean, either one of them in a problem that you want, but it's just another form of it. And then let me see what we have here. So this definition of HS right here, we call this HS as, let me write it down. Okay, I just write it down here. So this is the shaft work here. This is the definition for it. And then uh, the head is a kind of energy per unit weight. So um, energy per unit weight is going to be if you just write all of the unit and then simplify it, then you get length, which is the unit of length is meter, right? Then this is how we quantify the amount of head involved. And then also if we have I don't know if I just need, okay, let me just save also here, and I'm going to show you that also in the question that I'm going to solve. So let's consider we have a turbine that is in the control volume, and then it means that the work is negative because it is associated with the shaft work out of the control volume. And then if we have a pump in the control volume, it is positive because it is associated with the shaft work into the control volume. This is also important, and this is why I wanted to mention them here. And then also, if we look at this equation here, and we say that this is a loss here, right? So it, in other words, we can, this is loss here that we don't have it in the Bernoulli's equation. So this is why Bernoulli's represent the maximum useful of energy. The maximum useful energy. And I think that's it. That's what I wanted to tell you about the conservation of mass. Um, I know there are lots of equations here, but when we solve 2 or 3 problems, then you can see that how easy this is. So see you on the next video.